Alright, now let's do the last 5 problems of practice exam 1B. This question is about the belt of stability. We want to know what's true about this. So just the thing to note here, we've got the number of neutrons plotted on the y-axis and the number of protons plotted on the x-axis. The black boxes here represent stable isotopes. For elements about 1 through 20, you'll notice that the stable isotopes have about a 1-to-1 proton and neutron ratio. But after that, as the elements get heavier and heavier, you'll notice that the belt of stability skews itself up toward more neutrons. They're kind of like a nuclear glue of sorts. If an element, if an isotope has too high of a neutron to proton ratio, as represented by orange, it'll tend to undergo beta decay. Whereas if it doesn't have enough neutrons, then it'll tend to undergo electron capture or positron emission. Finally, for our really, really heavy isotopes, generally speaking, atomic numbers 84, polonium, and beyond, those are good candidates for alpha decay. So let's see which of these statements are true. A 1-to-1 neutron to proton ratio is ideal for maximum nuclear stability for all elements on the periodic table. Well, nope. In fact, that's really only true up to about number 20, as we said before, so that is false. B, isotopes above the belt have too many neutrons. During decay, neutrons are converted into protons. Well, too many neutrons, that is what happens above the belt, where there are more neutrons than the ideal amount. And in order to help satisfy that, we go through beta decay, which turns a neutron into a proton. So I like that. So the last ones. Isotopes below the belt have too many neutrons. No, that's too few neutrons. We can eliminate that one. Isotopes that decay via positron emission convert neutrons into protons. Nope, that's describing beta decay. Positron emission turns a proton into a neutron. And then finally, no element undergoes alpha decay unless bombarded with neutrons in a nuclear reactor. No, that's not true. Alpha decay occurs spontaneously. In fact, uranium is a major alpha emitter, so we get a lot of helium actually from pockets where uranium ore is found. So choice B for the win. Okay, this question is on mass defect, and so we're in essence doing the mystery of the missing mass. There's mass, it's going to be missing. Where did it go? Let's find out. So if we look at iron, so iron is element number 26, which means it has 26 protons. And iron 56 would have 56 minus 26 or 30 neutrons. So we have here the mass of a proton and the mass of a neutron given. Let's see how much iron 56, theoretically, what its mass should be if we take the sum of its individual parts, the protons and neutrons. So we've got 26 times 1.0072765 AMU. That will be the mass contributed by the protons, plus 30 times 1.0086649 AMU. That'll give us the mass contributed by the neutrons. And let's see what this ends up being total. So that it equals 56.449136 AMU. Wait a minute. What? How in the world can the sum of the mass of the neutrons and protons be less than the actual observed mass of the nucleus? The mystery of the missing mass. Well, it turns out that some of the mass is kind of shaved off. It's converted into nuclear binding energy to hold together the nucleus. So the amount of mass that's missing is called our mass defect, or delta M. So the delta M is just going to be equal to the mass that we observe, the 55.92068 AMU, minus the mass of the protons and neutrons. So, upon carrying out this, we'll get the difference is 0.528456 AMU. And this is technically negative, but the negative is just kind of arbitrary. It's, kind of the perspective that you're looking on this. So the mass of the actual nucleus is 0.528456 AMU less than the mass of the constituent nucleons that make it up. Okay, so this is our mass defect, but now we need to convert this into kilograms per mole. So we're going to need some calculations here. So we need to remember that this 0.528456 AMU discrepancy is the amount of mass missing in one measly nucleus. So now let's just do a whole bunch of dimensional analysis. At times might seem kind of oxymoronic because we'll be both dividing by and multiplying by Avogadro's number, but in order to get the units correct, that's what we need to do, so that's what we're going to do. To convert to grams, we need to divide by Avogadro's number. In 1 gram, there are 6.02 times 10 to the 23rd atomic mass units. Then to convert to kilograms, we need to use the relationship that there are 1,000 grams per kilogram, so that'll cancel out grams. And now our units will be in kilograms per nucleus, but we want kilograms per mole. So there are 6.02 times 10 to the 23rd nuclei for every mole, so that's going to effectively cancel out nuclei, and then we'll have everything in kilograms per mole. So this will end up equaling 5.28 times 10 to the negative 4th kilograms per mole. That is our mass defect. This problem has a whole bunch of scenarios and asks which one was not catalysis. So all these are catalysis except for one, that's choice C. It says holding a lit flame next to a balloon filled with hydrogen and oxygen resulted in an explosion, formation of a fireball, flaming gas, and a rise in temperature. That is not catalysis. That is using the flame to overcome the activation energy. And then once the reaction starts going and you get the combustion, well then there's a whole lot more energy because of the heat released, and then the reaction goes from there. In this problem, we're given a giant celestial rock that we need to find the age of. It's got uranium and lead-206 in it. Let's find out how old it is. So first we need to keep in mind what the decay process is going on here. So our process is the uranium decaying into lead-206 over time. So the star of this reaction is the uranium. It is our reactant. And in this problem, we're given the N sub T right off the bat. We're told it's got 68 milligrams of uranium-235. So that's the amount remaining. That is our N sub T. 68 milligrams of uranium-238. Our goal is to find the N sub 0 because we have the half-life of this decay process. So if we know the N sub T and the N sub 0, well, we can find the time that must have elapsed while this decay took place and find out how old this rock is. So, what we need to do is find that N sub 0. And to do that, it's helpful to consider a little bit of a cartoon here. So we have this giant block that consists of lead-206 and uranium-235. That's it glowing green. Okay? So, what we need to consider is, since it's the uranium that's decaying, has this uranium-235 been here since the beginning? Yeah, it's old school uranium, okay? So it's been part of this block since the beginning of this decay process. The lead, however, has not always been lead. What did it used to be? Well, it used to be uranium. So let's consider what this block would have looked like before the decay process. So this 68 milligrams of uranium was there since the beginning. Now our goal is to find out how many milligrams of lead, or rather the 22 milligrams of lead, how many milligrams of uranium that was before it decayed. And to do that, we can set up a simple mass ratio. We have 22 milligrams of lead-206, but is that what its mass was before it decayed? No, it would have had a little bit more mass when it was uranium-235. So let's set up our stoichiometry. For every 206, that should be milligrams of lead-206 that we have, well, when it was uranium, before it decayed, it would have been 235 milligrams of uranium-235. Now with this mass ratio, our units of lead-206 will cancel out, and we'll end up with 235 milligrams of uranium-2... Oh, no! Nope, no, wait, sorry. This is the same number, 25.1 milligrams of uranium-235. There we go. Okay, so now we know how much uranium decayed into the lead, and now we can easily find the initial mass of uranium in our block. We just need to add these two masses together, the 25.1 milligrams plus the 68 milligrams. And since at time 0 this is all uranium, let's just make the whole thing glowing. Okay, so our N sub 0 was the 68 milligrams of uranium that have been there since the beginning of the decay, plus the 25.1 milligrams that decayed into lead, which gives us a total of 93.1 milligrams for our N sub 0. Now we have everything we need. Let's solve for the time. Remember that K, our rate constant, is equal to 0.693 divided by the half-life. 4.5 times 10 to the 9th years. Impressive. And this is going to equal 1.54 times 10 to the negative 10th years to the negative 1. There's our K. Let's solve for T. We have the natural log of 68 milligrams divided by 93.1 milligrams. That's our N sub T divided by N sub 0 equals negative K, 1.54 times 10 to the negative 10th years to negative 1 times T. So taking our natural log, we get negative 0.314. So then we're going to divide both sides by negative K. T is equal to 2.04 times 10 to the 9th years. So about 2 billion years old. That's notable. Okay, in this problem, we're comparing the relative value of K for a catalyzed and an uncatalyzed reaction. So this problem is just going to end up being an algebraic powerhouse. So let's do it. It's based off of the Arrhenius equation, where rate constant K equals our frequency factor A times e to the negative activation energy divided by RT. So what we want to do here is set up a ratio. The K of the catalyzed reaction is equal to AE to the negative E sub A, the catalyzed activation energy, divided by RT. And we're going to divide this by the K of our uncatalyzed reaction, K uncat, which would be equal to AE to the negative E sub A of the uncatalyzed reaction divided by RT. So we're making kind of a big assumption here, but to simplify the problem, and that assumption is that the frequency factor A sub E, or A, does not change for the catalyzed and uncatalyzed. Many catalysts work by changing the frequency factor. Let's just assume here that doesn't, though, for the sake of simplicity, to find this ratio. You get E to the negative catalyzed activation energy, 27.5 kilojoules per mole. Now, considering this is in kilojoules, we need to keep that in mind when we divide by our gas constant R, 0.008314 kilojoules per mole Kelvin. And then we've got to multiply that value by our temperature, 353 K. Okay, we'll come back and we'll solve that in just a moment, but just for completion's sake, we're going to fill in the bottom part of this. So remember, we set up a ratio here. So K cat divided by K uncat is equal to that entire thing divided by, whoop-pow, this entire thing. Now, as long as we don't try to haste this and do everything at once in our calculators, we should do just fine. So I'm going to simplify both the numerator and the denominator before proceeding. So all of our units are going to cancel out, and we're left with e to the negative 9.37 on the top, and e to the negative 22.15 on the bottom. We're really, really close to solving this algebraic powerhouse. This is equal to... This ends up being about 350,000 times faster, so 3.5 times 10 to the fifth. Yowzas! Wow, catalysts really do speed up reactions. That's notable. And that is the end of practice exam 1B. You did it! Woo! Okay, so keep up the hard work and make sure to dominate the real exam.